نعم أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الحمد لله والصلاة والسلام على رسول الله. This is lesson 2, the continuation of what we started in lesson 1 for third week SS2 SS2 chemistry. So we stopped from the former notes, from the former work. We talked about the occurrence and the discovery of oxygen. We look at the occurrence and the discovery of oxygen. We have looked at laboratory preparation, the industrial preparation. We have looked at its chemical and physical properties and the tests. Now I want to move forward looking at oxides. Oxides are formed when elements combine with oxygen. We have different kinds of oxides. We have what we call the basic oxides. We have the acidic oxides. We have the amphoteric oxide. We have the neutral oxides. We have the peroxides. Even we have higher oxides. Number 1, what are basic oxides? Basic oxides, they are oxides of metals, like the group 1 and the group 2 metals. When they combine with oxygen, they form their oxides, like sodium oxide, magnesium oxide, and the likes. When these oxides that are formed, when they react with acid, they form salt and water only. So due to the fact that they can react with acid and form salt and water, that's why they are called basic oxides. As you can see in this equation, sodium oxide reacting with hydrochloric acid giving us sodium chloride and water. We also have what we call the acidic oxides. Acidic oxide, they are oxides of non-metals. Non-metals like carbon, sulfur, phosphorus, and the likes. These oxides of non-metals, they react with alkalis, that is soluble bases, to form salt and water only. These acidic oxides, they are also referred to as acid anhydrides. They are also referred to as acid anhydrides because they can simply dissolve in water to form acids. That is why they are actually called acid anhydrides. Example of such acidic oxides are carbon 4 oxide, triazosulfate 6 oxide, and the likes. Now looking at this equation under number 2, acidic oxide, we have CO2 combining with NaOH. We have Na2CO3 and H2O. Another example of the oxide that we have is amphoteric oxide. When we say amphoteric, from the word amph, anytime you see amphi means two. So when something is amphi, like amphitheater, amphibian, going to biology a little bit, when we have amphibians like toad or frog, they are amphibians because they can live on land and on water. That's why they are called amphibians. So amphoteric means they have two different kinds of properties they can exhibit. They are also metallic oxides, just like basic oxides, but they can behave both as basic oxides and as acidic oxides to form salt and water. Example of such metals that can combine with oxygen to form amphoteric oxides are aluminium, zinc, lead, and tin. Zinc oxide, for instance, can react with H2SO4, as you can see here, to give us ZnSO4 and H2O. It can also react with NaOH in the presence of small amount of water to give us Na2Z and OH4. Now, what is this one trying to tell us is that, so it is behaving, ZnO is behaving as a kind of acidic oxide in the second example, is behaving as a basic oxide in the first example. So ZnO being and what? Being an photonic oxide. Same thing, aluminum oxide can behave in that two way. The same thing, lead oxide and thin oxide. Moving forward, we also have another example of oxide we call neutral oxide. These are neither acidic or not basic. So they are neutral to litmus. When you take a litmus paper, these kinds of oxides that when they react with litmus paper, they do not turn red litmus paper to anything. They do not turn blue litmus paper to anything. That it remains like that. Such oxides include H2O, CO, and N2O. H2O, that is water. CO, that is carbon 2 oxide, and nitrogen 1 oxide. So moving forward, we also have what we call peroxides. As we know that oxides are formed when some other elements react with oxygen. Now, when it's happens, or if it happens that some oxide contain a higher proportion of oxygen than the ordinary oxides, so they are called peroxides. They are called peroxides, like Na2O2, sodium peroxide, calcium peroxide, barium peroxide. So all these, they are examples of what? They are examples of peroxide. Why? Because they contain higher proportion of oxygen than the ordinary oxides of those metals. Now, we also have what we call the higher oxides that would look at, like the lead hydroxide, like manganese 4 oxide. We also have a dilead 2 lead 4 oxide, that is Pb3O4, also known as red lead oxide. We also have higher oxide like iron 2 diiron 3 oxide, because they contain higher proportion of oxygen. That is why they are called higher oxide. Coming back to this peroxide now, how do you form peroxides when they react? Let me come in that perspective. Peroxide, they have reactions they show with acid like H2SO4. When peroxides, barium peroxide for instance, react with H2SO4, it's going to give us barium sulfate and hydrogen peroxide will be released. This particular reaction that peroxides show, that when they react with dilute acid, they can yield hydrogen peroxide, a very important compound. Now, as you can see here, the BaO2 plus H2SO4 giving us BaSO4 plus H2O2, it's a kind of reaction that we can use to show the preparation of hydrogen peroxide in the laboratory. That if anybody asks you to describe how you can prepare hydrogen peroxide in the laboratory, you can use peroxides or higher oxides like barium peroxide plus H2SO4. So reacting with the barium sulfate and reacting with H2SO4, giving us barium sulfate, and H2O2 is produced. That is for preparation of hydrogen peroxide. Now, industrially, but before I go to the industrial preparation of hydrogen peroxide, there is something I want to emphasize here. The peroxides that are actually formed, they are formed, like I have said, when you have more oxygen reacting with metals. So I don't need to emphasize too much on that. When you have more oxygen reacting with metals, that is when you have what? You have the higher oxide being formed. Now the higher oxide, like barium oxide, cannot react with acid to produce hydrogen peroxide. That is for laboratory preparation in a small scale, in a small quantity. You now want to prepare hydrogen peroxide, the peroxide of hydrogen, in the industry. How do you go about that? It can be prepared or it can be produced industrially by the oxidation of propan-2-ore. Is an alkanol with oxygen under slight pressure. As you can see in this equation, under Roman figure 1 here. So propan 2-ol, CH3, C into bracket 2, CHOH plus O2, giving us CH3, 2, and CO. So when that takes place, there will be removal of hydrogen from the propan 2-ol to give us propanone, and hydrogen peroxide will be released. That is the first industrial way of doing that. Then secondly, we can also get that if you want to prepare hydrogen peroxide in the industry by the oxidation of substituted anthracene. The oxidation of substituted anthracene. Anthracene 9,10-dione is a form of ketone. It's a form of ketone. So there's an equation here that shows that. So to my left hand side here, we have a ketone. So this anthracene 9,10-dione will now be hydrogenated to form the diol. So this diol reacting with more oxygen will lead to the release of hydrogen peroxide, as you can see in this cycle here. So coming from the right hand side, you have what we call the anthracene 9,10-dione. So the arrow that goes down and curves up gives us the diol to the left hand side. Then the diol, when it loses oxygen, when oxygen enters into it, more oxygen enters into the diol. So then it can give us what we call the hydrogen peroxide, as you can see coming out on the top arrow here. So that particular reaction, it's showing how you can produce hydrogen peroxide in the industry on a large scale. Now the hydrogen peroxide that is produced, we should know the nature of the compound is that it can be easily decomposed by light. So what we'll have to do is that we'll keep the hydrogen peroxide in a dark glass bottle, so that having produced the compound, it will not just be decomposed again back to liquid and ordinary, and oxygen will be liberated straight. So we need to keep it in a dark glass bottle so that light will not be able to penetrate it. Or we put it in an aluminum container just to prevent its decomposition. So moving forward, what do we see as regards the physical properties of hydrogen peroxide? This hydrogen peroxide we're even talking about, how does it look like? Hydrogen peroxide is a pale blue syrupy liquid. It is a weak acidic solution when it's put inside water. That means when you put this hydrogen peroxide inside water, it forms a weakly acidic solution. Then it also boils. When it boils, it gets decomposed at about 150 degrees Celsius. That's for hydrogen peroxide. Then it freezes at about minus 0.9 degrees Celsius. All these are pointing to the physical properties of hydrogen peroxide. Chemically, looking at its chemical properties, hydrogen peroxide can be decomposed to water, like I've said, and oxygen. That one takes place exothermically. Hydrogen peroxide, it can serve as an oxidizing agent in some reaction, and it can also serve as a reducing agent in some other reactions, depending on where it finds itself. If it finds itself in the presence of a more oxidizing compound, a strongly oxidizing agent, or a strong oxidizing agent, it will behave as a reducing agent. That is hydrogen peroxide. But if it finds itself in the midst of a compound or a substance that is less oxidizing compared to its oxidizing nature, so it will behave as an oxidizing agent. So A here shows the decomposition of hydrogen peroxide to water and oxygen gas. B shows how it can behave as an oxidizing agent, while it behaves as a reducing agent. So in this C, hydrogen peroxide uses, what is this used for? It is used as an antiseptic. It is used in bleaching delicate materials such as silk, wool, wood pulp, etc. That other compound or substance like chlorine can make them to become bleached and damaged. So you can use hydrogen peroxide to bleach them and they will still retain their good quality and properties. So third, it can be used to improve lead paint quality and color. So the lead paint, that the white color that we have in the lead paint, so can be easily tarnished if we expose it to light. But when you now make sure that because when it's exposed to light or to atmospheric hydrogen sulfide, so it can change such paint to black substance. What do I mean? White lead paint, it contains lead 2 triisocarbonate 4. It gets blackened when exposed to atmospheric hydrogen sulfide. Now, because the lead 2 compounds present, they are converted to lead 2 sulfide. That is why you are going to see the lead 2 paint changing the color. If you now treat such a paint, if you have treated it with hydrogen peroxide, it will make it to restore its quality and color. That is that. Then we can liquid hydrogen peroxide. It provides liquid hydrogen peroxide. It provides oxygen for burning of fuel in space rockets. Then it is used in making compounds like sodium triiodochlorate 3 and some other organic peroxide, which are used for starting polymerization reaction. So joining of monomers. We will dwell on that very much when we are treating organic chemistry and we are looking at the hydrocarbons and the likes, inshallah rahman. Now moving forward, ozone. Ozone is an unstable triatomic molecule. It is actually formed from oxygen. It was discovered in 1839 by Chm2. Yes, Chm2 discovered the ozone. This ozone is also an important allotrope of oxygen, as described by J. Soret in the year 1866. So how is it formed? In the atmosphere, it is formed from atmospheric oxygen by lightning flashes when there is thunderstorm. So lightning flashes will make it to be formed. So how? When the oxygen molecule breaks into two, it forms the atoms. The one atom will form a radical and will now go and join another oxygen molecule, so forming O3. One oxygen molecule will be broken by the light to form atoms. One of the atoms will stand in form of radical and will go and join another oxygen molecule, so to form O3. So ozone exists in the layer of atmosphere, up in the atmosphere at about 20 kilometers above the earth. What is it doing there? It is serving as a protecting shield from ultraviolet rays, some rays that are damaging to our life on earth. So it is this ozone that is protecting us from that. It is prepared in an ozonizer. If you want to prepare it from oxygen by passing an electric discharge through it, as you can see here. So like I have just said, so we have the O2 combined with ordinary atomic radical that has been formed from another oxygen molecule. When it joins to another oxygen molecule, so it will form what we call the O3. O2 join with a radical formed from another oxygen molecule, so we form the O3. Then if you look at ozone is a pale blue gas. It's a pale blue gas at standard temperature and pressure with a characteristic smell like that of dilute chlorine. That's how it smells. It is poisonous if it is too much, especially when we have it around 100 parts per million. Yes, it can also be poisonous. So it can decompose into ordinary oxygen on heating, even just on standing. It is very reactive. You cannot just put ozone down like this. If you put it down, so it would get decomposed to oxygen molecule. It's a more powerful oxidizing agent than oxygen. Yes, it is more powerful when it comes to oxidizing compounds. So ozone, what is it used to do? Ozone is a good bleaching agent used for ventilating when there is little fresh, especially in underground. Those people that are doing mining or underground tunnels where a train is passing. So there can be little oxygen underneath. So if you don't want people to be suffocated, you can take ozone there so that oxygen can be readily got from such ozone that is present under the ground. So especially for miners or for tunnels that have been passed underground. Use as an as using disinfecting water and sewage purification. Yes, you hear some water say ozonized water to make sure bacteria do not grow there, to make sure microorganisms do not thrive. So ozone can be used to do that. And in sewage purification, then it is also used in air conditioning plants. So these are the uses of the ozone. In short, we have been able to talk about the oxides, the types of oxide that we have, the basic oxide, acidic, amphoteric, the neutral, and the peroxides. Then we have also been able to talk about the hydrogen peroxide, laboratory preparation, and the industrial preparation, its chemical properties, what the reaction that it can undergo, then its uses. So then we have been able to look at ozone. So we pray Allah subhanahu wa ta'ala grant us the knowledge, wisdom, and understanding, and bless our knowledge. May Allah bless our school, may Allah bless our teacher. So till we meet next time, I pray Allah subhanahu wa ta'ala be with us, be with our parents, be with our students, be with our teachers. Put back in all our endeavors. Wassalamu alaikum wa rahmatullahi wa barakatuh.